Alright, today we're going to have a look at the normal distribution. Now, some of the questions in the past few exercises have involved long and arduous calculations. For example, if we wanted to know the probability of getting at least 3 heads, we may calculate the probability of 4 or 5 or 6 heads. Of course this is doable, but what about for large sample sizes? For example, what if we wanted to know the probability of getting at least 3,000 in a sample of 10,000? So the central limit theorem is something you may have seen in advanced maths, and it tells us that the distribution of any event with a large enough sample size follows a normal distribution. I think it's one of the most cool theorems in all of existence, really. Any distribution of any event follows a normal distribution for a large enough sample size. So there's a theorem that tells us that for very large values of n, a binomial distribution is approximately a normal distribution. So for a normal distribution of mean, mu, and variance sigma squared, it's denoted as x belongs to a normal distribution mean, mu, variance sigma squared. So for large values of n, a binomial distribution becomes a normal distribution. So recall that for a binomial distribution, mu is equal to np and variance is npq. So therefore, for a binomial distribution Bn is approximated by the normal distribution npq. Now the approximation is less satisfactory if the distribution is skewed and more satisfactory for a large number of trials. It's common to require np to be greater than 5 and nq also to be greater than 5 for a normal distribution. So a coin is tossed 120 times, and x is the number of heads. Find the probability the number of heads is greater than 12 using a binomial distribution, first of all. So to find greater than 12, really we want 13, 14, 15, 16, and so on. So we're going to have 20 choose 13 times by 1/2 to the power of 13 times 1/2 to the power of 17 plus 20 choose 14 times by 1/2 to the 1/2 to the power of 14 times by 1/2 to the power of 16 plus ... plus it takes us forever 20 choose 20 1/2 to the power of 20. Okay. Now if you type all of that in, you're going to get a very long calculation. You're going to get 0.132 and it's going to take you ages. So this is where a normal approximation of a binomial distribution comes in handy. So the probability of at least 13 heads, we're looking at the probability of x, or at least 13. Now before we finish this question, we're going to introduce the idea of continuity corrections. So a binomial distribution is discrete. That is, we are considering an integer number of events which is defined as an upper and lower bound. So if we had 20 people, the lower bound would be 0 and the upper bound would be 40. But a normal distribution is a continuous distribution which creates a problem. A binomial distribution looks like this, whereas a normal distribution looks like this. And also, when we would have looked at Maths Advanced, you cannot, on a normal distribution, find the value of something at a particular point because it doesn't make sense. Normal distributions gives percentages. For example, 50% of the results lie here. 68% of the results lie in here. So if you wanted to know the probability of someone being just here, you can't. You have to choose a minimum of 2 points, and then you could do some work in here. So if we approximated a binomial distribution as a normal distribution, suppose we're interested in information for greater than 40. Well, a normal distribution starts at negative infinity and goes to positive infinity. Whereas this binomial distribution might end at exactly 50 and start at exactly 40. So suppose we wanted to know the probability at exactly 40. An approximation all the way to infinity may not include starting at exactly 40. It mightn't start, if we approximated this curve, it mightn't include exactly 40. So it might cut off some of our answers because we're approximating a discrete variable to a continuous variable. So because of this, we apply something called a continuity correction. This helps us make sure the desired upper and lower bounds are definitely in the calculations. So if we wanted to approximate this variable, if we started the distribution here and then the distribution looked like that, well, since we've gone a bit below where we wanted to start, we're definitely going to include the starting point in it. So the continuity correction for a normal approximation of a binomial distribution is 0.5. That is, we subtract 0.5 from the lower limit and add 0.5 to the upper limit, except when either limit is plus or minus infinity. Realistically though, we can't have plus or minus infinity in a binomial distribution because that's not discrete. This though only applies to small values of n. So if we want the probability of being at least 13, we're actually going to approximately consider the probability that that x is greater than 12.5. And that's to account for our continuity correction. Okay, so we want to know the probability that x is greater than or equal to 12.5. Okay, to do this, we need to now find the mean and the standard deviation of this experiment. So the mean is equal to NP, and that's because a binomial random variable is approximately normal, so that means the mean and variance and the standard deviation are the same. So 20 times by the probability of success, which is a half, which is 10. And the standard deviation is going to be the square root of 20 times a half, which is a square root of 20. So now we're going to apply our z-score formula. Z is equal to x minus mu on sigma. So x, we're looking at 12.5 minus 10 over 2.24. And if you do that, you get 1.11. 1.11. Okay. So really, we're looking at the probability that z, because we've applied our z-score, is greater than 1.11. And if you have a look, remember though your z distribution tables give you less than, so we need to go the probability 1 minus the probability that z is less than 1.11. And if you look at your z-score table, you'll get 1 minus 0.868, which is 0.132. That's a bit of a quicker way to do that answer. Okay. Didn't we just do this one? A coin is cost 20 times. Yes, I just did that one. Okay, I have to fix that. Okay, in this next example, a continuity correction is not necessary because n is very large. Let's have a go. Let's use the continuity correction, though, in part B and see what happens. So we've got compute that p is between 3,300, x is between 3,300 and 3,400. And we're going to do this using a normal approximation of a binomial random variable. It would be very, very tricky to do this using the binomial theorem because you would have to go 3,300 plus 3,301 plus 3,302. So really what we're doing is having a look at, in the introduction, I feel like I've missed out on something. I think I've missed out on something in this example, so I need to state that n is equal to 10,000. I accidentally cut off something. N is equal to 10,000, P is equal to 1/3, and Q is equal to 2/3. That's better. Okay, so let's have a look at the mean and standard deviation. So the mean is going to equal 10,000 times by 1/3, which is 333.3, repeating, and the standard deviation is going to be the square root of 10,000 times 1/3 times 2/3, which you get 47.14. So we're going to compute these z-scores. So let's do the first z-score. We might call it z1. That z-score is going to be equal to the score of 3,300 minus the average of, I haven't got enough threes there, 3,333.3 on the standard deviation of 47.14. And we do that, we get minus 0.706, and the second z-score is the same thing, except we're looking at the upper bound of 3,400 minus 3,333.3 over 47.14, and we get our upper z-score is equal to 1.145. So really we're looking at the probability that z, because we're doing a z-score, is minus 0.706. I'll write that a bit better. And that's to be less than 1.145. Okay, now to compute that, you're just going, this is the probability that z is less than 1.145 minus the probability that z is less than minus 0.706. And if you use your z-score table, you're going to eventually get 0.6816. Okay, I need some more room for this. What's the next thing? Binomial. Okay, now part B, we're going to do the continuity correction. So we're going 0.5 above and below. So we were looking at being between 3,300 and 3,400. So now we're going to be between 3299.5 is less than or equal to x is less than or equal to 3,400.0.5. So we've gone 0.5 above and below. And we're going to do some new z-scores. If you do that first z-score with that new number, you get minus 0.7177. And the second z-score is going to be 1.4248. So really now we're looking at the probability that z is between minus 0.7177 and 1.4248. And if you do that on your calculator, and use your z-score table, so the probability that z is less than 1.4248 minus the probability that z is less than minus 0.71776, you get 0.6859. Okay, so the difference in probabilities, we've got 0.6816 versus 0.6816. Looking at the difference in these probabilities, this one is probably more accurate, but we're going down to the, this is our tenths, hundredths we're going down to the thousandths. No one really cares about that in probability. It's insignificant difference, so we don't really need to do that in this case. Okay. So we can also use a normal approximation to calculate a binomial coefficient. So recall that for a continuous distribution, we can't determine the probability of a single value. So we're going to approximate 100 choose 53. Let's see if a calculator can do that. It can, but it's not pretty. Using a binomial distribution, 100 probability is a half. So I typed this into Excel and into my calculator as well, and it gave us that. So that's what we're trying to prove that it is. So the way we're going to do this is we can't determine the probability using a single variable. So we need to do a continuity correction by going 0.5 above and below. So we can't go probability x is between 53 and 53. We can't do that. Maybe with some calculus, some advanced calculus you could, but we can't. We need to go 0.5 above and below. That's the best we can do. So 52.5 and 53.5. So this continuity correction is showing us that we're going a tiny bit above and a tiny bit below, and that will get us approximately the value in the middle. And this is actually how calculus was developed, but that's a whole different idea. Not specifically through this, but the idea of going a tiny bit above and a tiny bit below. So if we calculate those z-scores, well, the mean is 100 times a half, which is 50. And the standard deviation is the square root of 100 times 0.5 times 0.5, which is 5. So if we calculate those z-scores, z1 is going to be 52.5 minus 50 on 5, which is 0.5. Let me quickly check that. 52.5 minus 50 on 5, 0.5. And Z2, we're going 53.5 minus 50 on 5. What do we get? 0.7. So really we're looking at the probability that Z is between 0.5 and 0.7. So we're going to calculate probability using our z-score table that z is less than 0.7 minus the probability that z is less than 0.5. And if you do that, you get 0.066574. Okay. So what that is telling us is that the coefficient, well, we know that the sum of the coefficients of a line of a binomial on Pascal's triangle is 2 to the power of n. So the sum of all of them would be 2 to the power of n, which is 2 to the power of 100. And the probability that we're getting 53 is this here. So if you do that, you get 8.438 times 10 to the 28, which is pretty close to our approximation. All right, thanks for watching.